wants to stop by. So I guess I'll say, since you have both lectures, you want to stop like by. It's your time system.
Okay. Yeah, that sounds like a good idea. Yeah, thank you.
Maybe let's start. Okay. So we just introduce our network. So we have actually this afternoon both teachers will be by Peter. So Peter Graham is a professor at Stanford University. So he's working on the standard model physics in general. He has many creative proposals to solve different problems of standard model. In particular, you have heard about the cosmic relaxion as a new possible new mechanism to address the electroweak hierarchy problem. And he also pioneered in applying novel techniques to detect dark matter, in particular axion and ultralight dark matter. He's a proposer and co-PI of CASPER, Cosmic Axion Spin Recession Experiment, and Dark Matter Radio. And he got a New Horizon Prize in 2017. So without further ado,
great.
I should say that Peter will only be here today and tomorrow. So, so take the opportunity. Okay.
Yeah, thank you. Thanks, Gigi, and thanks to all the organizers for inviting me. And very sorry I can't stay longer, but please do feel free to just come and ask me, talk to me anytime the next couple days. Okay, so I'll talk about some ideas we had and ideas that the community has had for experiments looking for axion and ultralight dark matter. I want this, hopefully, to be a pedagogical introduction, as the organizers asked. So definitely not an overview, okay? I'm not even going to try to be complete or anything. That means I'll leave out a lot of experiments. I apologize if I leave out your favorite. And necessarily, I'll also sort of unfairly slant the experiments I talk about more towards mine, solely because it was easier for me to prepare those for the notes, and also, honestly, because I know them much better than I know other experiments that I'm not as involved with. So it would be certainly much easier for me to answer any questions on experiments that I know better. So just with that preamble, so don't expect an overview of the field or anything. It has, in fact, as I'll try to convey, I'm really excited to say this field has really kind of blossomed in the past 10 or so years. It's really grown huge. I'm constantly learning now about new experiments that I wasn't aware of. So I really couldn't possibly talk about every one. Each one by itself would probably take a whole lecture. Okay. And I hope you'll interrupt me all the time and ask lots of questions. I prepared probably way more material than I can cover in 4 lectures, which is fine. I'm happy to cover whatever fraction of it we get to. So I'd much prefer that whatever I'm saying is clear. So if you have any questions, especially if I say something confusing, definitely remember that's my fault, okay? But you got to let me know. I don't necessarily know if I've said something that doesn't make sense, okay? But do please feel free to stop me anytime, or if you're just curious about something else, even if you have a question related to what I'm talking about, that's fine. All right. So I want to start by talking about ultralight dark matter detection in general. And in fact, I'll say ultralight dark matter direct detection. I think you're going to have lectures by Ben Safdie next week, or maybe in 2 weeks, who will talk about lots of astrophysical and cosmological probes of this kind of dark matter. So I'll really be talking about experiments here on Earth in the lab to directly detect this kind of dark matter. And let me first say, I think pretty much everyone is in particle theory, but I'll stick with h bar equals c equals 1. So just to remind you, of course, that means 310 to the 8 meters is 1 second. And also, just in case you don't have it memorized, let me say that means that 0.2 GeV times a femtometer is 1, okay? Consequence of this. And just in case you don't have it memorized, that's easy to remember because 200 MeV is the nuclear physics scale, and femtometer is the size of a nucleon, okay? And that's an extremely useful conversion I use all the time. In fact, my advisor, Savas, claimed that something like a quarter of his salary was due to that relation. It seems fair. All right. The experimentalists actually, particle theorists tend to work in these EV units. Experimentalists don't love it as much, but I'm proud to say I have managed to convert. I've turned several of my experimental colleagues to the dark side, and now they even think in EV units. All right, and then also, so I'll be talking about electromagnetism, so we'll use the Heaviside Lorentz units, which are the units I think used in most field theory textbooks. But just to remind you or tell you, if you don't know, the easy conversion to remember there, so experimentally we'll often talk about Teslas. That's what you'll hear from experimentalists all the time. When I see Tesla, then I think 200 EV squared. Okay, so that's what a Tesla is. All right, so now it's easy to convert units. And now we don't have to worry about the damn SI units anymore. All right? Okay, so let me leave that up. Walk all the way over here. Okay, so ultralight dark matter detection. So let's think about dark matter in general. I think you've already been hearing a lot about dark matter from Yonit. But let me say, I like to think about dark matter just asking, okay, what are the possible range of values for the dark matter's mass? So we know dark matter is something new beyond the standard model, right? Even if it's a modification of gravity or primordial black holes or something, you need something new, right? Something new in the standard model. I'll consider the possibility there really is just some new field, some new kind of particle, which is acting like matter, clumping in our galaxies, et cetera. So then we know it has to have some mass, right? But we don't otherwise know very much about it. In fact, the mass can range anywhere from approximately 10 to the minus 22 eV or so, all the way up many, many, many orders of magnitude. Let me maybe label the Planck scale here, 10 to the 19 JeV. And leaving an arrow beyond, because of course you could even have dark matter much heavier than the Planck scale. You could have primordial black holes all the way up to maybe solar mass or so. So there's many, many orders of magnitude uncertainty in what dark matter is, right? We really don't know. I'm mostly going to be talking about what I'll call ultralight dark matter. I'll kind of cut it about here or so at a mass of around 10 eV, and I'll be talking about everything on this side. Okay, trying to directly detect dark matter or some component of dark matter if it has a mass in this 23 orders of magnitude. All right. So even just chopping off and tackling only this one part of the problem seems pretty crazy, right? That's a lot of orders of magnitude to go looking over. So that's a big haystack, right? But one of the things I hope to convince you over the next 4 lectures is that actually, really excitingly, in the past 10 or so if you went back about a decade, we would have looked about here. And the width of the search would probably be about the width of that chalk line out of this number of orders of magnitude, maybe even smaller. Okay? That was the state 10, 15 years ago, all right? And what I want to convince you is that actually now, because a lot of people got really interested in this problem and realized this was an exciting problem to work on, and that at least right now, there were these new tools, precision measurement, as I'll tell you about, which would actually let us access potentially this whole range. So really excitingly, there have been a ton of new ideas in the past decade or so. And we've now got experiments that are at least new ideas, or in many cases even actually now beginning experiments, actual hardware in the lab, starting to probe all across this mass range. And of course, not surprisingly, you need a ton of different experiments, right? The sort of experiment that's looking for dark matter over here is probably not going to be able to look for dark matter over here. They're very different. Okay, so that's kind of the big picture, and hopefully we'll fill that in. Hopefully that becomes more clear as I go through these 4 lectures. All right. But so let me just tell you or remind you, for ultralight dark matter, the kind of poster child candidate is the axion. Okay? And so axions, depending on exactly what you mean by the word, will live anywhere in here, or just the QCD axion maybe lives somewhere like there. Whereas on the heavier dark matter side, the kind of poster child dark matter candidate is the Wimp. I'm sure you've heard about WIMPs, and hopefully someone else will be describing direct detection of heavier dark matter. So let me pause for a second, though, and say, I said we know almost nothing about dark matter, but I did draw this as a hard lower bound. Actually, it's only a hard lower bound on the dominant component of dark matter. A subcomponent could even be lighter than this. But it is a hard lower bound, we believe, on the dominant component of dark matter. I think Yonit was going to have discussed this already. Is that correct? Did she get to this already or no? Yes? No? Thumbs up, thumbs down, maybe? Thumbs up. All right, perfect. Thank you. OK, so then hopefully she told you that what happens here at such low masses is that the dark matter becomes very, very big, very fluffy, very quantum mechanically big, and so very difficult to fit into the gravitationally collapsed structures that we see in our universe, for example, dwarf galaxies. OK? So as a warm-up exercise, if you already did this with Yonit, apologies, but it's a good warm-up for everything I'm going to say, so let's do it again. As a warm-up exercise, let me ask you, how big is this dark matter? OK? So that's a question for you. How big is dark matter if its mass is 10 to the minus 22 eV? OK? So I'm going to try asking a bunch of these little questions to you throughout the lectures. It's not just me talking for 5 hours and hopefully wakes you up and lets you actually do something. And also, we'll just do short little exercises to make sure you're following along. I would suggest if you can each turn and talk to the people next to you, because actually, as hopefully people have told you, but the point of summer school, in my opinion, is to get to know each other, not really to listen to lectures. Well, maybe that's useful too. But seriously, I went to Tazi many years ago, 15 or something years ago, more. And still, many of the people who are at my Tazi are still my friends and colleagues today. You'll know many of these people throughout your whole physics career. Okay, so it's good to get to know them. So chat with the person next to you. I'll give you a minute or something. See if you can answer this question. And what do I even mean by this question? Okay. All right, sorry, I usually won't give you enough time to maybe actually finish, but it's a lecture, we got to keep moving. So let me tell you what I think or what I meant by this. So what I mean is, well, when we're down here, when we're at such low masses, quantum mechanics really matters. The dark matter particles become really big. It can't fit even into, let's say, a dwarf galaxy. Okay, so what does that mean? What's the relevant scale there? Well, I'd say the relevant scale is the de Broglie wavelength of the dark matter, which is roughly 1 over mv, its mass times whatever velocity it has. Okay. now, I'll evaluate that in a second, but actually, why is that? And in fact, in particular, another common thing if someone says, I was purposely vague in saying how big is it, the other natural length scale for that mass would be 1 over m, right? The Compton wavelength. Maybe there could have been other things too, but why is it the de Broglie wavelength? Okay? And the answer is just think the uncertainty principle. All right? So if here's my dwarf galaxy, and I'm trying to cram some dark matter particle that's gigantically big into it. This is a bizarre regime to think in, but this is what happens when you get down to such light masses. Okay? Well, we know quantum mechanically it'll have some wavelength, right? And I can give it a wave packet and try to crush it down. But the more I crush it down, the more I restrict its delta x. What happens? By uncertainty principle, you can yell it out. Delta p goes up, right? So this is really just the application of the uncertainty principle. Delta x at minimum has to be 1 over delta p, right? So if I try to crush it any smaller, the delta p will go up, right? So what's really happening is inside the dwarf galaxy, I have some big spread in momentum of each dark matter particle, or of all the dark matter particles, if you like, in the wave function. Well, why can't I just make delta p go up? Well, I could crush it down and make delta p go up, but shortly after that, the dark matter particle would no longer be in the dwarf galaxy, right? Because if the velocity is higher than the escape velocity, it's gone, right? So I'm absolutely limited by whatever the escape velocity of this galaxy is. By the way, for a dwarf, I think that's something of order 10 to the minus 4. By the way, all the numbers I give you in these lectures will be twiddles. I don't think I'll ever write a real equation. I'll let you fill in actual numbers and factors of 2 and such. But that means if you try to crush the dark matter so much that its velocity gets above 10 to the minus 4, forget it. It's escaped from the dwarf galaxy, right? So then we say the dark matter the size of it is set by 1 over its momentum dispersion, right? 1 over its delta p. So this is 1 over m delta v. And if you plug in 1 over 10 to the minus 22 EV. By the way, I have terrible handwriting, so if you can't read something I wrote, please let me know. Okay? 1 over 10 to the minus 22 EV times 10 to the minus 4. And then if you multiply by our favorite relation over there, 0.2 GeV Fermi, femtometer, 10 to the minus 15 meters, then I did this. Then I got about 2 10 to the 19 meters, okay? If you just multiply. And that's roughly a kiloparsec in the favorite astro units. So indeed, look, that's just about right. That's somewhat smaller than our galaxy. You may know that we're about 8.5 kiloparsecs from the center of the Milky Way, and dwarf, so the Milky Way is a little bit bigger than that, even the visible part. But dwarf galaxies are, of course, smaller than the Milky Way, so very, very roughly, at the level to which I'm working, that's about right, indeed, okay? So you can see why this 10 to the minus 22 EV is roughly the lower bound. If the mass was any smaller than this, the wavelength would get much bigger than this. Couldn't make collapsed dwarf galaxies, okay? Okay, is that clear? Questions on that? Or objections? All right. Good. Okay, so that's sort of a warm-up because it was exactly this kind of thinking, right? Normally we don't think of dark matter as being too big to fit in a galaxy. Its wave function as being too big to fit in a galaxy, right? It's kind of weird. But when we're talking about ultralight dark matter, you should reorient yourself to that kind of thinking, okay? That's sort of getting a feeling for what's going on in this part of parameter space. All right, so now let me jump to my actual problem, which is direct detection. How do we try to directly detect such dark matter in the lab? Okay, have it interact with our lab apparatus. And so for that, as I said, I kind of wanted, do we have another board? Yes. I kind of wanted to divide this parameter space at 10 eV. So let's say for direct detection. To the right, I'll kind of hand-wavingly call this particle-like dark matter. All right? In particular, for a Wimp, for example, 100 GeV, you have about the density of dark matter locally, right? So you have about 1 Wimp in about this amount of space. So if the Wimp is dark matter, there's one, right here in my hand right now. Okay, and that's it. And they're tiny, right? They're 100 GeV or whatever they are. They're very, very. They're actually their de Broglie wavelength is very, very, very small, right? So here they're really in this more particle-like limit. And indeed, as we know, as people have been trying for a long time, one of the best ways to look for it, I should say, is by doing some single hard, high-angle scattering event. Dark matter comes in, whacks your detector, deposits some energy, ionization or scintillation or whatever it is, right? And this is what the big Wimp direct detection experiments are trying to do, for example, right? So that's a great way to look for it, and the Wimp experiments have done a fantastic job, obviously plowing down many orders of magnitude over the years. In those kind of experiments, for example, in LZ, things like that, there's an experimental threshold for the amount of energy you need to deposit in order to be visible, which is usually about a keV. Now, let me just pause and say, as you may know, that was sort of the way it used to be when people were looking more specifically for dark matter right around 100 GeV. Now people are actually trying to look even lighter, and so make experiments that have even lower thresholds, which is great. Hopefully you'll hear some talks about that, either at TASI or in your future. I won't talk about that. But just an example, let's say LZ or one of the big experiments that has a threshold of around keV. What does that mean? Well, that means for the dark matter to possibly be visible, I would need it to carry enough. Let's say if it's just normal elastically scattering WIMPs, there would be other models too, as you may know. But just for a normal elastically scattering dark matter particle comes in, smacks a nucleus in my detector, it can't possibly deposit more than its kinetic energy, right? So I certainly need its kinetic energy to be bigger than about a keV. And since locally, the virial velocity in our galaxy is around 10 to the minus 3, that means you can see that this is good for looking for dark matter whose mass is bigger than very roughly GeV. Okay? Is that clear? Questions so far? All right. So that's great, right? But that's not going to work over here, right? Well, you can see these super light, ultralight dark matter candidates have way too little kinetic energy. In fact, we really shouldn't think about it as individual dark matter particles coming in and depositing their energy at all, or not. Let's say, let me retract that. Not in this way, where I talk about some individual particle coming in, scattering, and leaving its kinetic energy in the detector. Okay, so for these, you needed maybe what I would call more canonical particle-like detectors, things that were, a bit more like the detectors we build at colliders and things like that, right? Looking for single hits, tracks, ionization, whatever it is, right? Over here, on the ultralight side, we're going to need something very different from the way particle detectors were traditionally built, okay? So over here, let me call this wavelike, or sometimes I call it field-like dark matter. And to get a idea of what's going on over here, let's think back to this example of the size of the dark matter. Okay, so let's say I have some ultralight dark matter. Well, really, we just realized maybe I should be thinking quantum mechanically instead of thinking of it as a little dot, a little point. I should think of it as some wave packet, right? Those are supposed to be little wave packets flying around, okay? They've got some finite extent. They've got some finite spatial size, right? I can't crush them too far, right? Okay, fine. So as the dark matter mass gets lighter and lighter and lighter, how many are there? Well, this is here a little quick exercise for you. Let's say I tell you the local dark matter density, which is about 0.3 JeV per cubic centimeter. A number you may know is also 0.04 EV to the fourth. Okay. Oh, yes. Sorry. Thank you. Good. Is that a little better? Yes. All right, good. Thank you. Yes, yeah, please let me know. Yes?
So in this scenario, are you imagining that, for example, the detector on Earth is like moving through this dark matter dark matter in the galaxy?
Yeah. Absolutely. So exactly. So you should imagine, okay, I build my detector here on Earth, and then there's just this whole bunch of dark matter everywhere, and it's flying every which way through my detector. And then in this example, occasionally one of them will hit, do a hard high angle scatter, leave some energy. Exactly. So that's what I'm sort of imagining for this case. And I haven't told you yet what I'm imagining for this case, but it's going to change that picture a little bit. Good. Yes. Thank you. Yes.
So the reason you can think of the velocity of dark matter as the zero velocity is because it interacts with the standard model of particles so little that the velocity is only determined by gravity of the galaxy as a whole.
Excellent. Yeah, great. Yeah, great. That's a great question. So the question was, why can I think of it? Why do I know the dark matter's velocity? We haven't even seen the dark matter. How do I know? I think that's maybe a fair way to rephrase it. Why am I saying it's the virial velocity, right? Well, and he makes an excellent point. The dark matter, in principle, the dark matter could actually be interacting with things itself and standard model particles, and that could shift the velocity distribution. And in fact, as you may know, there's a wide literature talking about that. It's a very interesting subject. I'll skip it completely right now. Okay. However, let me say, on the side I'm talking about, and also even on the particle-like side with the more traditional candidates, it interacts so weakly that it doesn't almost ever interact with a standard model. In fact, that makes one limit on how strongly it can interact. So exactly as he says, the dark matter is interacting so weakly, all it's doing is virializing gravitationally. So as the Milky Way eats little clumps, and that's how the Milky Way grew from eating lots of smaller clumps, accreted them, and then they all got stretched out and virialized all around our galaxy. And so we expect the dark matter to just have the virial velocity. Absolutely, exactly. All really need, so I'll be using that a lot in the lecture. All I'll really need, though, is that it can't have more than the virial velocity. And that's because that's also, at the twiddle level, that's also the escape velocity. So I know it can't have more than that. There's got to be a whole bunch of it with velocity that or less. Exactly. Very good. Yeah, great questions. Yeah, thank you. Any other questions? Yes?
So with this ultralight dark matter, assuming there's so much of it because it's so light, so it needs to fit this 0.0 or 0.3 GeV per centimeter. Won't all the wave functions be entangled with each other? So why does it make sense to think about the size of a single wave function?
Excellent. Very good. Very excellent. And this is essentially what I'm getting to here. And let me change one word though, which is I wouldn't call them entangled. That would depend on actual quantum mechanical correlations between the dark matter particles, which would depend on your production mechanism, things like that. But what I definitely know about, even if I don't know anything about the model, I've been very general about the model, right? This is just quantum mechanics so far. I haven't told you, this applies to any model I write down, right? So long as it obeys quantum mechanics and gravity. But what I would know, exactly as she says, right, is these things will get so big, they're definitely sitting on top of each other. They're definitely overlapping, right? They get to be in the same place. So evaluate that. Let's say I take one cube, which is a de Broglie wavelength on a side. Write down a quick expression for how many dark matter particles are there in that cube as a function of mass m, using this row. You don't have to do the numbers, you can just leave it in symbols. Okay, so try that. You can talk with the people next to you or whatever. Oh, sorry. Exactly. Yep. Very good. I'm coming to that. Excellent. Mm-hmm.
So as you know, it's variabilized because of the gravitational dynamics, right? You mentioned kind of at the start that this was potentially due to some gravitational, the dark matter mechanics itself was due to something happening above the gravitational scale potentially. So how are we so sure we know how it interacts with gravity?
Good. If you like, you could say it's a hypothesis, although everything is interacted that way, so it's a pretty good one, I think. But even if it was a primordial black hole or something much heavier than the Planck mass, primordial black holes would still follow the laws of gravity. I mean, the regular black holes we see do follow those laws. So anything, no matter what, will follow the same laws of gravity, basically. It's universal. In fact, unless its quantum wave function is so big that stops the gravitational pressure from pulling in. As long as the wave function is small, you can treat it as a particle and do your freshman mechanics or whatever.
So the only concern in placing is on its way.
Exactly. All right, sorry, in the interest of time, I'll interrupt you. Sorry about that. But it's good if you got a chance to think about it. So the number of particles in this de Broglie wavelength cube, right, is the number density, which is the energy density of dark matter over the mass of dark matter, right, times the volume here, which is lambda de Broglie cubed, which is 1 over mv cubed. Okay, let me raise that up a little bit. All right, is that clear where I got that? Okay. So what I want you to take from this is the scaling with mass, for example. This is a very fast scaling with mass, 4th power. All right, and if I plug in these numbers, 0.04 eV to the 4th, and the virial velocity 10 to the minus 3, then as a function of m, you can convince yourself this is just 10 eV, roughly 10 eV over m to the 4th. Okay, you can basically see it. This rho is about 0.1 eV or so to the 4th, but v is 10 to the minus 3. Okay, there's a 3/4 or whatever in there, but roughly it goes up by a couple orders of magnitude. It goes to 10 eV. Okay, you see that? So what does that mean? That means, look, when m gets to be less than 10 eV, there's more than one dark matter particle per de Broglie wavelength cubed, right? You see that? So first of all, as actually she pointed out over there, immediately that tells you it can't be a fermion, right? I can't do high phase space density packing of a fermion. It must be a boson, all right? So we'll only be talking about scalars and vectors in this lecture. And as m gets ever smaller than 10 eV, you can see the phase space density. This is the phase space density, right? The amount of packed per de Broglie wavelength cubed. It goes up really fast. So at 10 eV, it's about 1, right? But look, when I got to 10 to the minus 22 eV, that's a hell of a lot of particles per de Broglie wavelength, right? And even not very far below 10 eV, it's a hell of a lot of particles per de Broglie wavelength. Okay? Is that clear? All right. This is one of the most important points I want to make, because what does this mean? This means this is why I don't want to think of them as individual, well-separated particles, right? Totally different limit than the Wimp. This is why I call them this like a field-like or wave-like. Of course, all right, you all know particles and waves, same thing. We know quantum mechanics. But I and many other people have found it much more useful to think in this field or wave picture when trying to think of ideas for directly detecting dark matter. And I hope what I'm going to try to show you throughout these lectures is when you start thinking in this field picture or this wave picture, many of these ideas are really quite simple. Whereas when you try to view them in the particle picture, I don't think we would have thought of them. Okay, it made it much easier when you had the right picture, much easier to think of these new ideas. Yes.
So they couldn't be fermions. Could it be fermion condensate?
Good. Yeah. Good. So maybe in principle. So she asked, could it be a fermion condensate? Maybe in principle, but you do have the problem that let's say. Even with a fermion condensate, it depends how it's coupled. But certainly if it's acting at all like a weakly coupled system, then no, right? Then you haven't really just like if I make an atom out of a proton and electron, although that's a boson, I haven't actually disguised the fact that it's got fermions in it. If I actually try to pack too many together, they'll know. Now. However, let me just leave it there, but say it's a good question though, and with creative model building, perhaps maybe there'd be a way around it, but certainly not if it's acting like anything like a weakly coupled bound state would. Good. Yes. Other questions? All right. Okay. So what is this telling me? This is telling me instead of thinking of individual well-separated particles, I want to think about this as some big collection. Okay. I want to think about this as one field, as a classical field. All right, this has such high phase space occupancy that I don't need to think about individual particles. I can just think about it as one net classical field. Okay. This is good too, because it means what I can look for when I'm trying to design direct detection experiments to look for this kind of dark matter. I can look for dark matter that isn't just single dark matter particle came in and deposited its energy. That's a very small mass. It's a very small amount of energy. It might be very hard to look for. I can look for the more classical coherent effects of all the dark matter acting together. All right. I like to use the analogy. In fact, I think it's a very good analogy that I'm going to try to keep drawing over these lectures. That these detectors for this ultralight dark matter are going to be a lot actually like gravitational wave detectors. right? When LIGO is observing gravitational waves, you don't talk about it as absorbing individual gravitons, right? I mean, it is doing that, but it's a bit of a silly picture. You're never possibly going to see the quantization of gravitons, right? You think of it as just some big classical gravitational wave, right? Some metric perturbation coming in and wiggling LIGO's masses, okay? Or a lot of these experiments are in many ways similar to a radio. When you think of a radio absorbing some E&M wave, right, you just think of the E&M wave you wrote down in undergrad physics. You don't think of absorbing, individual radio photons. Of course, it's doing that, but it was a lot easier to, if you were the electrical engineer designing the radio, it was much easier to just write down Maxwell's equations with a classical EM wave, right, and design the radio using that, Jackson style. Okay. Okay, so we want to picture this as a classical field, and because it's so important, I even have my little slide here. So instead of these small, widely separated particles, think about it as just, for example, some scalar or some vector field filling space. So I really do mean, right here, if there's a vector, for example, there's just one direction, and the dark matter vector A mu is pointing like that way. Okay, right? Or if it's a scalar, it's just got some value that's even in many ways simpler, but it's just some oscillating scalar field, right? That's why I call it wavelike. Picture it as some wave filling space. Yes.
So in this classical field picture where all of these dark matter particles are kind of this single field, how could you satisfy like astrophysical clumpiness?
Great, good. So exactly. So and that definitely is. In fact, I should say, I only mentioned dwarf galaxies, but there's actually a whole host of structure formation constraints, and they kick in sort of around here. Anything, so long as the de Broglie wavelength of the particle is small compared to whatever the relevant astrophysical scale is. So, the smallest gravitationally collapsed things we've got are basically like dwarf galaxies. But whatever scale I'm talking about, so long as the de Broglie wavelength is small compared to that, it'll act just like a point particle, right? Quantum mechanics doesn't matter. You just do your freshman mechanics or whatever. But once it gets too big, then the quantum pressure term, as they call it in these equations, starts to matter. And so you'll actually get, there have been a whole host of nice bounds that a lot of people have worked out, or let's say nice ways of probing this kind. I should say, by the way, sorry. I think Yonit said this hopefully, but we call this end the fuzzy dark matter end of the parameter space, probing this kind of fuzzy dark matter. So that's been a whole literature in itself. And I won't go into it at all, but it's very interesting and well worth looking into. I have a lot of conversations actually with my colleague, Risa Wexler, who does things like this about axions. Good, yes?
So we found that these are really highly packed, but how come they managed to do this like coherent?
Ah, good. Excellent. So that's because, let's say, in this very high phase space occupancy limit, that's where the classical approximation is good. For almost everything I'd want, I can make that approximation. And a good example that sometimes confuses or is confusing, but actually a good example is a laser. Now, a laser, someone has worked to put them all in the same state, but actually they're not all in the same state. No laser is perfect. Every laser has some frequency spread to it. Okay? I mean, so actually, as I'll tell you a little bit later, just down the hall here, people make some of the best lasers in the world at Gilla. But nevertheless, no laser is infinitely narrow. So they're actually a whole bunch of states adding. But if they're close in frequency, they all add up to something that you can approximate that looks like this, a sinusoid. Okay? I'll go into more detail on this probably in one or two lectures. So it's a great question and non-trivial. But let me say for now that you can convince yourself, if you like, it's really in fact just a basic property of Fourier analysis. In fact, it sort of has nothing to do with physics, just has to do with adding sines and cosines. If I add a whole lot of sinusoids of around the same frequency, even arbitrary phases and arbitrary directions, they add up to one sinusoid of about that frequency, or something that looks very similar to one sinusoid, okay? So even if I imagine adding a whole lot of different little wave packets, and this is by the way, totally not obvious, and I'll really get into more details of this probably in 2 lectures, but it's a great question you asked now, so let me just say now, so it's okay to consider it, to make this classical approximation for almost everything we want to do. By the way, there would certainly be corrections to that. So I'm going to talk about detection. So LIGO, when they detect, they map out some waveform, right? You've seen some waveform. And similarly, I'll be looking to detect this oscillating dark matter, this wave here, and I'll be in many of the experiments would actually be able to map out some waveform of the dark matter. Would be able to they would sit at one point and see this oscillation. But what you could ask, and I think this is a bit what your question is getting at, maybe that's very good in this low mass limit. There's very high phase-space occupancy, but what does it look like as I start to break that, as I start to go towards 10 eV? Then your question in a sense becomes very relevant, and in fact, it looks ever more quantized, ever more chunky. I don't see it as just a perfect wave, okay? And it will naturally dissolve into seeing more individual hits as the mass gets higher. Anyway, okay, that was a bit of a tangent. Great, okay, good. Let me just see if I said what I wanted to say. So one other thing, which is, as I mentioned, this will be a low amount of energy to deposit in a detector. And also, as we'll see, such light particles are very heavily constrained. Their coupling to us, I should say, is very heavily constrained. Right? If they were fairly strongly coupled to us, we would have seen them a long time ago. It doesn't take much of a collider to produce particles 10 eV or less, right? So they have very weak couplings to us. So we're going to need very high precision experiments. All right? And in fact, it's really useful that we can look for the collective effect of all of this dark matter acting together. It isn't totally obvious, or I should say it isn't obvious at all from anything I've said so far, except maybe the analogy with a radio and with gravitational wave detection. But the key thing you want to focus on when you're thinking about detection is not so much the mass, but the frequency. And I'm going to talk all about this, but I just want you to keep the following numbers in mind. If I convert 10 eV to a frequency, it's just a little above optical, right? Electron volt is the energy of an optical photon, right? So an optical, as you may know, is about 10 to the 15 hertz or so. So let's call this about 10 to the 16 hertz. It's a high frequency, but we can absolutely access optical things in the lab. That's something we can play with. We couldn't really play with much higher frequencies. At that point, you need to start walking over into more high energy techniques. But we certainly have high precision things that work in the optical, right? And all the way down to 10 to minus 22 eV, which someone coincidentally happens to be about an inverse year. And I would say that's very lucky, because that's about the lowest frequency you're going to access in the lab. Not that you can't actually look for something that's DC, that doesn't have a frequency. But if I want to see it oscillating, which is a hallmark of dark matter, as we'll discuss, and if you're the experimental grad student in the lab, you don't want to wait, too much more than a year to finish your PhD, right? You want to see a few oscillations of the thing. If it was a millennium or something, if it was a million years, which it easily could have been. Look how many orders of magnitude there. That would have been tough luck, right? So we sort of got very lucky. We got very lucky that somehow the dark matter falls in this gigantic frequency range between optical and an inverse year. But those are human frequencies. We can and have accessed them with high precision experiments in the lab. Okay? So that's a kind of top level point I want you to keep in mind as I go through. I'll show you lots of examples of that. Yes?
Is it a content?
Aha, very good. Yeah, thank you. I should have said that. I snuck that in. Didn't think about that. That's right. This is just the mass converted to a hertz. That's it. I just literally converted to hertz using those conversions. And you have to watch the 2 pi, but anyway. No V, and I'll get to that in just a second. Very good. Yeah, I have not explained that. Good. Yes. Any other questions? Yes.
So thinking about these extremely long wavelengths and I guess short frequencies, how much does the position of the Earth sort of in the dark matter wind matter if this is on the order of months?
Very good. Yeah. That's a great question, and let me actually address it. I'm going to come to it, but in 2 lectures. We will absolutely care about the properties of this, including particularly the coherence properties of this, and the Earth's motion through that will affect that. But it'll be more clear if I can address it in a lecture or 2. Yes. Very good. Thank you. Excellent. Great. All right. Okay. So now we've sort of said what the field looks like. Now, how do we go about trying to see it? So in fact, this is addressing the question that he just brought up. It's a very light dark matter field. I haven't said yet anything about the model. But very model independently, it has a mass. If it didn't have a mass, it wouldn't clump into galaxies. So dark matter must have a mass, yeah? So I know at the very least, it has some, I'll drop the half because I'm not keeping 2s in this lecture, potential that goes like m squared a squared. Oh, I'm going to call the dark matter scalar A because that stands for axion. You can call it phi, doesn't matter. I'm not even meaning any particular model yet, just a scalar, okay? Actually, I could write, maybe it also stands for capital A, and then it would also be true of a vector, all right? Either way, it's the same mass term. All right, So here's my potential as a function of the field A, right? And I've said I should think of it as a classical field. So I should just write down the classical field equations of motion. So just like we see there, here at this point in space, dark matter has some value. The A field has some value. Maybe it's this, right? But what's it going to do? Well, I've drawn the picture suggestively. You know what it's going to do. You know what the equations of motion for just a quadratic potential do, right? The thing's just going to oscillate back and forth in the potential, right? Just to be clear about what that means, let me even, this picture, I want to start even a little bit simpler than this picture. Let me even first just imagine the dark matter field is completely homogeneous. That'll be, for the masses I'm talking about, more or less true on laboratory scales anyway. So here I am in the lab. The experiment I'm going to build basically see a homogeneous scalar field. It would maybe only be much longer scales where you'd see this kind of spatial variation. Okay? So it's basically just dead homogeneous. And then the field value at each point in space just goes negative, positive, negative, positive. That's what it's doing right here. And that's what my experiment is trying to tune into. Okay? So what I'm trying to see then is that my scalar field A, or my vector field or whatever, just goes like some amplitude cosine mt. And there's the answer to his question. That's why I converted the m's by themselves just to frequencies. There's no v in this. There's no v in the potential, right? It's just the potential term for a massive scalar or a massive vector, right? Just oscillates with the frequency of its mass. So it looks sort of a simple, pretty trivial formula, but it's actually really important. So let me pause for just a second, right? So this is what you're looking for. You're looking for right here in space. I have some scalar or some vector field, right? But it's oscillating with some frequency. All right. And to begin with, I'm gonna pretend it's really just a perfect cosine. I'll change that approximation in a lecture or two and get to her question. But for now, just imagine the perfect cosine, one frequency. Okay. Is that clear? Any questions on that? Yes.
So this is not assuming it starts off at non-zero values.
Ah, very good. In fact, actually, let me not answer. Great question. Let me not answer that question because I'm about to ask you that question. but let me just say. Well, okay, I'll kind of answer it. If it was here and not, well, this does go through 0, by the way, of course. But if it was here and not moving, it wouldn't have any energy density. Okay, that was sort of a hint for what I'm about to ask you to do. So in other words, I'm assuming there was a dark matter production mechanism. So it's certainly true that a massive scale, if I just put a massive scalar in Lagrangian, it wouldn't have to be produced by the universe. That depends on the model and things like that. Although, by the way, there is a non-zero amount of simply gravitational production just from existing in general relativity, from inflation onwards. But anyway, I won't talk about that in these lectures. But it's an interesting story. I'm happy to tell you later. So actually, there always has to be some non-zero value of this field, but it might be very small. It might not contain much energy density. But I'm going to assume that it had a production mechanism. All these dark matter candidates I'm talking, or the Axion, for example, does have a great production mechanism. That's why we're interested in it. I'm not telling it to you. I think you may hear it in another lecture. I'm not sure. But yes, exactly. And so all I'm assuming is that it has some non-zero value now, here, locally, right here in my lab where I want to see it. And so it's oscillating. Okay? And in fact, apropos of his question, I want to know what that value is, right? So I can see if I can see it. So how do we calculate it? Well, that's a question for you. Go ahead and calculate it. And I'll just remind you that the energy density contained in a scalar field is the kinetic energy, 1/2 a dot squared. I'm assuming no spatial derivatives right now, right? Plus the potential energy, and that's it. So now you tell me, how big is A naught? Try, you can talk with the people next to you and stuff. Oh, yes, please, yeah.
So we were talking about how the scales can be about like an inverse year. And when you say a year, to me it sounds like we're going around the sun. So we've been talking about lab scales a lot, but our lab is also kind of moving around a lot. So we're really kind of like we're taking measurements all along, right?
Very good, yep.
So could that improve our...
It does sometimes matter. There are, for some of the experiments, I won't talk about it much in these lectures, but for some of the experiments, there are annual modulation effects that matter. One thing I'll say though, for the base picture, it doesn't in some sense change the base. It does matter for some like ways of seeing it. It doesn't change this base picture of it because you can really just think, okay, what's the relative velocity between me and dark matter? And the velocity of the Earth around the sun, what you can compute, is something like 3 × 10⁻⁵. so it's much slower than the virial velocity. So your relative velocity is still dominated by virial. But it's a useful thing to keep in mind, and multiple times I have used it in my research, this going around the sun, definitely. All right, as usual, I won't give you enough time to actually do it. The main idea is you had a chance to think about it, so you could see if something I was saying was confusing or not. Well, if I want to know how big it is, so at the top of its oscillation, it's all potential energy. Down here, it's all kinetic, like we teach the freshmen, right? Back and forth. So if I want to know the amplitude of its oscillation, I simply say, okay, at the top here, where the value is A0, how much energy does it have? Well, it's all potential there, so its energy is like m squared a squared, so that must be equal to the energy density of dark matter, 0.3 Jev per cubic centimeter. Okay? Is that clear? That's how you find the amplitude? Yes. Yes, 10 to minus 3 is the local virial velocity of dark matter is 10 to minus 3. That's right. That's right. Although, yeah, yeah, I would need a gradient term in here for the energy for sure. Exactly. That's right. That's right. But I can neglect it. Exactly. Exactly. Very good. Although I will get back to the spatial gradient of A, but in a lecture or two. We'll start leading order just with this, but it will become important for sure. Good. Yes. Okay, so then if you just plug in numbers for this, I can give you the answer. It is, so the amplitude is, you can see, in fact, let me write it as root rho over m. This is a very useful thing to keep in mind. Okay, square root of the amplitude of the dark matter field is the square root of the energy density in dark matter divided by the mass of dark matter. In particular, remember this 1 over m scaling. That'll come back and be useful later, many times. Okay. At understanding some of the patterns we see. In numbers, this is 10 to the minus 3 eV. If the mass is order 1 eV, or at the other end of the range, it's about 10 to the 19 eV. If the mass is order 10 to the minus 22 eV. Okay? This is not a super meaningful number yet, but we're going to use it in just a second to figure out how detectable this dark matter is. But this tells you the size of the dark matter field here locally, right here in my lab. Okay? Is that clear? Good so far? This is the amplitude of the oscillation. That's right. That's right. This is the A0 term, the amplitude. Oh yeah, sorry. Because so good. Yeah, maybe I see the question. So this is the expression for the energy density contained in a scalar field, right? And at the end of the oscillation, it's all potential. In the middle, it's all kinetic. Somewhere else, it's some mixture. But I just evaluated the amplitude by going to the very end. But this is always the energy density. It just flops back and forth between being potential and A dot. And by the way, by kinetic, I didn't, I'm using the word two different ways. I didn't mean 1/2 mv squared, v the virial velocity of dark matter. I meant what is called kinetic energy in a field theory textbook, 1/2 A dot squared. Hopefully that was clear. So it would have, a field has kinetic energy even if it has 0 velocity. But it doesn't have 1/2 mv squared. Sorry, was that clear, what I just said? That was kind of confusing. Okay. Well, this row, there would always be some fixed total energy. As I lose potential, I just gain kinetic. So there's always some fixed total dark matter energy given by this formula. There will actually be some variation because of the spatial variation, but I'm not getting to that yet. Maybe let's chat afterwards. Maybe there's just a miscommunication. Yes?
So on the very low mass end where you have these just massive amplitudes, I would think you could have seen this somewhere.
Right. Good. And absolutely, exactly. And in fact, as you point out, the low mass end actually is in many cases, this is not a theorem, but in many cases it is easiest to see. So you'll see many of my limits will go like this on the plot. They'll be better at lower mass, and that's why. Absolutely. However, as I'll show you later, depends on the particular coupling I'm talking about, but essentially for any coupling, such a light particle has to be very weakly coupled, and I'll talk about why. So it's going to be still very hard to see. But a little easier at the lightest mass end, absolutely. Very good. Yes, great questions. Other questions? All right. OK. Sorry. OK. All right, so this is the field. This is what you're looking for, some picture like this. I should really box this. This is so important. Some field like this with amplitude like this. That's our signal. That's what we're looking for. But how can I possibly look for it? Well, now I need to ask, what is its coupling to the standard model, right? If it doesn't have a coupling to the standard model, I'm not going to be able to directly detect it. All right? There are many possible couplings, although luckily, the tools of effective field theory actually severely limit how many different possible, so at least as long as you believe the rules of field theory and things like Lorentz symmetry and you believe the gauge symmetries of the standard model are good symmetries, blah, blah, blah. So if you're willing to grant me that, then there are actually not that many possible couplings. In fact, I'm going to show you all of the leading order ones probably next lecture, OK? But there aren't too many. So I can just start picking them off and looking for them. So let me start with one that I think is a nice example to start with. For example, let's say my axion, or my random scalar field, whatever it is, has some coupling to the standard model that looks like some dimensionless number, GE, that'll be the coupling constant, times the axion field A. I'm doing leading order, so I'm just going to do A to the 1. And then it couples to the electron field like this. This is the low energy 4-component Dirac spinner of the electron in the standard model. Okay. So this is one clearly allowed coupling in the standard model, right? E bar E is neutral, so I can just write an A in front of it. All right. Then how do I look for it? So that's one possible coupling. So that's something dark matter could have. In general, you know the law of particle theorists, that if it's allowed, it should be there. So I expect this to be there at some level, at least if there isn't some other symmetry in the A sector which forbids it, which we'll get into a little bit later. But in general, I would expect such a coupling to be there. I have no idea how big this number should be, but anyway, it should be there at some level, so we should think about how do we look for it, and what are the limits on that coupling. Yes?
So since the E bar E is like a scalar and A is like a pseudo-scalar, if you write this kind of interactions, the A is not.
Very good. That's what I haven't yet said A is a pseudoscalar. Thank you, very good. And that's what I actually meant, unless there is some symmetry in the dark matter sector which forbids this, which it would if I required it to be a pseudoscalar. Absolutely. Although there was always at some level some CP breaking, even so. We haven't gotten to this yet, but just as a tangent since you asked, in case you guys know something, but if you know something about the axion, there is always some CP break. The standard model breaks CP, and so at some level, even for the generic QCD axion, this coupling would exist, but it'd be really small. But however, right now I'm talking about any general dark matter, and don't let my use of the letter A confuse you or anything. Right now I'm talking about any general dark matter, and you're right. When I classify the operators in just a second, this will be one for the scalar and not the pseudoscalar. But it's an easier one to start with, to explain. Good, yeah, great question. Any other questions? All right. So this is my question to you. How do we look for it? What do we see? So in particular, imagine I wrote this down, and I've just told you what A is. It's a classical field. You should just plug it into the Lagrangian, classical background VEV. All right. Let's say I have an electron in my lab. I'm one of these amazing AMO folks down the hall who I can just grab an electron and play around with it. I can throw it up in the air, catch it, things like that. What does this look like phenomenologically? What do I see with this? This is a little harder question. Chat with your neighbor and see. I'll give you a minute or two just to think about it. What is an electron in my lab, in my hand? Forget the fact that it's quantum mechanical. Let me just play around with it. What does it look like?
Yeah, like very low energy standards. Like Frankfurt's like experiments, maybe. Like where you.
And you just look for like something to its kinetic energy.
All right, I'm going to cut you off because this is actually a super general question. In fact, you could spend months or years thinking about this. Maybe some of you already come up with a new research idea, and you should write it up for how to look for this kind of dark matter. Let me tell you what I was thinking, okay? Which is, look at this. This looks a heck of a lot like the mass operator for the electron, right? Maybe some of you realize that. Just psi bar psi, right? And this is just a number in front. No, it's true this one is changing in time, but I'm not treating it as a field. I'm not talking about back reaction on the axion field. We should be so lucky to interact so strongly with the axion that we're going to back react on it. So the quantum mechanics of this field doesn't matter at all. It's just a classical background vev. It's just a number. So this is just a modification to the electron mass. Is that clear?
Yeah.
All right. But, yes?
Why do you say it's just a number?
What I mean is, although this is a quantum field, I'm not going to treat it as a quantum field. I'm just going to plug in its vev. Because the only time I'd only care about the fact that it's actually a quantum field if I could interact with if I could like source axions or something. And that I'm not going to be able to do. I'm working in such a weak coupling limit that I can really treat this as a background classical field. That's all I meant by just a number. So in other words, let me say exactly explicitly what I mean, which is I just plug in here GE, some number, some coupling constant, and then I just plug that in. A naught, and you know that's some number like this in electron volts, times cosine MT. So that's all I meant by just a number, like literally numbers I could plug in, right? This is some number I'm about to give you. This is a number we already calculated. Did that answer the question? Okay. Yeah. Okay, so yes.
But if we had kind of the 10 to the 19 EVs,
looks big. Very good. Exactly. So yeah. So let me say it's this, right? And then times E bar E plus whatever the actual mass of the electron is. In fact, let me remind you, it's about 511 keV, right? So exactly as he says, well, this A naught looks a little big. That's true. But in fact, as I was mentioning before, this GE is painfully small. Okay? It has to be painfully small because also, what would this do? You know, in fact, I'll show you this a little bit later, but you can maybe immediately see that if I drew a diagram like this, the scalar field would mediate a new force between the electrons, right? And we've looked for fifth forces of nature, and we haven't seen them, and we bounded them to really, really low strengths. And so that will be the best bound on this GE, at least at low masses, which I will show you in a couple, probably in a few minutes. Yes?
and kind of taking the higher frequencies of these things, if it's going to more massive, then would we also not see this like it averages up to zero?
Very good. Excellent. Good. So great thought. So as I said, would we not see it at high frequencies? Look, it could average out to zero. So good. This is exactly what I want to get into. So first, let's think, how do we look for this? Okay? Because in particular, that means that the mass of the electron is not quite 511 keV. It's also plus some going to be small. Of course, you know it has to be small. Correction, GE A naught cosine MT. By the way, as a tangent, exactly as he says is true, though, if this frequency is really high, really high above any experimental way we have of accessing such frequencies, which means maybe even above, TeV, since the LHC gets the TeV frequencies or energies, then this would average out, yeah? And so Depends how you would look for it, but at least this part of the effect would have no effect in an experiment literally looking to measure the electron mass. That's not to say there wouldn't be an effect of this, but it wouldn't be what I'm about to talk about. All right? Yes?
In that case, if this time scale is comparable to the experiment time scale, wouldn't, like that approximation I would think is not good, and then you would actually give energy to the electron.
Okay, good. This will also do other things, absolutely, other than simply oscillate the electron's mass. And that's true. I can look for those too, and we'll talk about at least one of them a little bit later, for sure. But one thing it will do is oscillate the electron's mass. And in particular, exactly what I'll do is try to make an experiment that's fast compared to this time scale so I can see it oscillating, exactly. Because if it was slow, as you said, well, this wouldn't be what I'd see, right? It would average out. It would average down. By the way, you can already see why I said that these frequencies were the thing to pay attention to, right? Because it's very different if the electron mass oscillates once every year or if it oscillates once every 10 to the minus 16 seconds. Yeah? It's a very different kind of experiment you need to look for it. All right.
One quick question.
Yes?
What, generically for experiments, what kind of ranges of frequencies can you hope to probe, even if it's like shifted out?
So you could be asking two different questions. For a particular experiment, any particular experiment has some range of frequency that it'll be best at, and I'm going to show you a bunch of examples, so I couldn't give a general answer to that question. Each experiment will just be really different. The different techniques are very different. I'll try to at least give you a flavor of that throughout all these lectures. Overall, though, my statement from the beginning is, overall, I think we can cover most of that range, which I think is a strong statement. Not totally proven yet, but we've had a lot of good ideas for covering a lot of that range. We, I mean the field, all the people working on this. All right, so as many of you are asking, how big is this? Yeah, how big a change to the electron mass? At low masses, or low frequencies, the bound on GE is almost mass independent from any orders of magnitude. I'll show you the real plot in a second, but the bound on GE is almost mass independent from any orders of magnitude. And it's roughly given by, where did it go? Here we go. 511 keV over 10 to the 30 EV. I phrased it in this funny unit so you can see it's the fractional effect on the electron mass. Okay? So now you can plug in and see how big this is. Maybe I'll spare you the arithmetic and do it for you. How big is this term here? The shift to the electron mass. So if I just multiply this GE by that A naught we just calculated, yeah? You can see that it's about, in fact, let me normalize out the 511 keV. So the delta ME over ME, the fractional shift to the electron mass. So this term over this term is 10 to the minus 33 for M around an EV. And it's 10 to the minus 11 for M around 10 to the minus 22 EV. Okay? So that's small, right? That's a small change. You can see why I want precision measurement techniques. Yeah? I'm not going to be able to just like toss an electron and catch it and tell, right? A part in 10 to the 11. By the way, for such high masses, this is not the bound. The bound is less stringent than this, so the true number would be higher, but it's still very small. Okay? Okay, so is this clear where I got this number? Yes?
So this 10 to 30 EV, is this characterizing current bounds, or where do you put?
Yeah, sorry. Yeah, exactly. This is current experimental bounds, which actually comes from the new force that it would mediate. So I'll show you that in a second, but it would need to be, the coupling needs to be this small to not already have been seen in, for example, torsion pendulum experiments.
I see.
I'll mention those a little later. So this is at the bound. So in other words, I'm hoping to entice some or all of you to come work in this area. Join us. So if you want to have a new idea for how to look, you got to beat this, right? Your idea has to be better, has to be able to see better than part in 10 to the 11 changes to the electron mass. Particular ones that oscillate with a very particular frequency. Okay? not just a DC shift. That, of course, is meaningless since I don't know the electron mass in the I can't predict the electron mass in the standard model anyway. But this is an oscillatory shift. Really not what you, by the way, this also illustrates, I kind of snuck it in here, but a key point, which is actually going to be true, like an important thing to keep in mind for a lot of the different ultralight dark matter detection experiments or examples, which is I had something that was a fundamental constant of nature, right? We always say the mass of the electron is written down in the PDG. It's a fundamental constant of nature, measured for all time, right? But oh look, the ultralight dark matter makes the fundamental constants of nature oscillate in time. This is going to be a very generic statement. We'll see this multiple times, okay? So that's what we look for. And that's really not what we expected. I mean, we before, prior to this, we didn't have a lot of people looking for an oscillatory electron mass, right? So that'll be a hallmark of this kind of background dark matter field. All right. OK, yes? I don't know that it's dark matter, or rather, I should say, I can tell from this, or if I believe the rules of quantum field theory at all, if there's an oscillatory number here in front of psi bar psi, I don't think I should write explicit time breaking in the Lagrangian. That would violate a lot of nasty things, energy conservation and other things. So imagine tomorrow an experimentalist says, I saw an electron mass that varies in time, right? It's a great question. What do I know? So I should repeat, sorry. Her question was, if I see this, how do I know it's dark matter? So I don't know it's dark matter, or actually, I don't know it's all of the dark matter. But what I know it's some should have been fundamental constant of nature, but it's oscillating in time. So immediately, everyone's first guess is, let's not break the rules of quantum field theory. That's been working great for decades, yeah? We should not just put in a cosine MT in Lagrangian. That's a hard breaking. Yeah, we should softly break it. We should put in a scalar field. And if you put in a scalar field, it should have a kinetic term. That's how it got these dynamics, how it can wiggle in time. And so it must carry energy density. And so what that experimentalist has seen, by seeing the oscillating electron mass, is there is some background scalar field. And it's oscillating time, which means, where did it go? It must carry energy density. I don't know that it's 0.3 jet per cubic centimeter. I don't know it's all the dark matter. In fact, that's going to be very, very hard to know. That's a true story about any dark matter. But I know it's part of it, at least. So great question. And by watching the coherence properties, I could maybe tell that it's non-relativistic. But I haven't talked about that yet. That'll be in a couple lectures. Yeah, that's a great question. Yes?
This estimation of the agent is only for local energy density.
Mm-hmm.
It means that different out of the universe with different oscillation and different amplitude.
Yes.
Is there any ways to see or use these facts?
Great question. So he asks, look, this is dependent. This A naught is dependent on the local energy density. Yeah. So different spots in the universe would actually have different values of this. So thank you. That's a really important thing to point out. And then he asks, is there any way to use this? So first, isn't that kind of cool? If I took my electron and I wandered out of the galaxy, okay, that's hard to do, but as a theorist, I can imagine, if I wandered out of the galaxy, all of a sudden its mass is different, right? The amplitude of the oscillation has gone way down. That's pretty cool, right? So absolutely, this depends on the local density, for sure. That's right. Now you ask, is there any way to use that? Let me turn it around. I don't know. Think about it. That's a great thought. see if you can use it. The low dark matter masses, as I'll discuss, but in a lecture or two, the low dark matter masses we're talking about have very long coherence lengths. So the spatial gradients are very low. So you'd have to go very far to see a change. Maybe, but well, in a sense, what I'll talk about just next lecture, though, we'll use that. There is a slight gradient even here, and we do use that. So maybe that will partially answer your question. Yeah.
Could you send one of these experiments out on Voyager?
In principle, for sure, absolutely. If someone gives me the money. Like I said, the coherence length is pretty long for most of the masses we'd be interested in. So for most of the masses, that wouldn't be a useful experiment. But maybe for higher masses, there'd be a reason.
Are these current bounds that you're talking about where the 10 to the 30 EV comes from, are those all from like Earth-based particle experiments as opposed to like early universe probes?
Great question. They're all from Earth-based like high precision experiments, like the Etwash group in Washington, for example, torsion balances, and anything else that looks for new forces. Cosmology limits are weaker for this particular coupling, although other couplings, absolutely, cosmology limits can dominate. Excellent. Let me see what time it is. OK. I think I'm basically out of time. So First, any more questions on this? Okay, so let me say, this is a really good, so I did this example in some detail. We'll do the next examples kind of faster. But this is a really good example. It illustrates a lot of, basically all of the key features of looking for ultralight dark matter, which is, I'm looking for some classical coherently oscillating field, scalar or vector, some boson as we said, right? And it will often do something like this. It will take some parameter, say, for example, a fundamental constant in the standard model, and cause it to oscillate in time. Or in general, maybe they won't all quite be like that. But in general, it'll be some absurdly tiny effect that I need some really high precision device to go after. Okay? So that's a good place to stop. When we come back for the next lecture in half an hour, I'll give you an example of, for example, how to look for that. In fact, a couple examples of how to look for this phenomenology. But we figured out the phenomenology of this ultralight dark matter. Okay? And in particular, as a sneak peek, you can try to guess ahead of time, think for yourself ahead of time what I'll say. For example, AMO techniques, atomic physics techniques, can be exceedingly precise. In fact, as I've mentioned, I'll even showing pictures of things just down the hall from here. That might be a good way to look for this. So let me pause there and let you think about that over the break, and then we'll come back in half an hour or so. And feel free to come up and ask if you have questions or anything.
I just wanted to introduce myself. I'm Anne Catherine.
Oh, hi. Nice to meet you.
I work with Surjit.
Oh, nice.
Yeah,
Oh,
and I
great.
think you guys
Cool.
have done some
Yeah,
work
I've known Surjit for many, many, many years.
Gotcha.
Great.
Thank you for answering all my questions. I know I
Yeah,
asked
of course.
a lot, so I
No,
really,
no
I really
problem. No
appreciate
problem. Of course, please. More questions, the better.
Thank you.
I don't want to just talk. Yeah.
Hi, I had a quick, maybe naive question about the potential that we wrote down. Is it possible to just couple the field to gravity and then offset the potential in